So here we want to find what we call the equation of the chord of contact. Now, this might be something you'll have to look at a couple of times because it's a bit of a weird concept, and sometimes it takes a leap of faith to do this one. So, just warning you. So let's have a look at what we're talking about. What we want here with a chord of contact is a line that will join 2 points on the parabola. Okay, and that's the contact where the tangents are touching that parabola. So we've got two tangents in the red here. Now, what we want to do is find the equation of those tangents. Okay, if that's the point x1, y1, and the point x2, y2. So well, let's do it for x1, y1 first. So we find our derivative of the tangent of the parabola, which is x squared equals 4ay. So we find our derivative function. And at the point x1, we get the gradient x1 over 2a. And the tangent then would be y minus y1, x1 over 2a, outside of x minus x1. So we've just subbed it in, we've got our point, we've got our gradient, and we've started to expand it out. So the 2a's are multiplied across there, we've got the equation, and we've got our expansion here. So now as we know that x1 all squared, so if we substitute x1 all squared in that part, that would give us 4ay1, because x1 and y1 satisfy that equation. So we could make that statement from the parabola. So instead of having x1 all squared, I'm going to put 4ay1 because I've got 2ay1 there. And then we're going to get to add all that across that side. So we get x times x1 equals 2ay plus 2ay1. Or we could write it as xx1, 2a outside of y plus y1, which is an equation of a line because you just got an x and you've got a y in there. So that's an equation of a straight line, which makes sense because we'll find the equation of the tangent. So that's the equation of that tangent there. That's why I've labelled it there. Okay. Now I haven't done exactly the same work to get this point, but we know because instead of x1, y1, we've got x2, y2. So we do exactly the same thing and just change the x2 and y2 as we go through. So that's why we get x times x2 outside of 2a y plus y2. So pretty similar ways we're writing that equation, but they're both tangents, and all it's changing is the point. So it doesn't really matter where the point is, where the tangents are. It's going to give the same similar equation. So we've written them up there. So the equation of the tangent at A is x times x1, 2a y plus y1, and at B it's xx2 equals 2a y plus y2. Now they both go through a point here, which we've labelled x0, y0. So when we do that, we can look at saying, okay, let's take this equation and substitute x0, y0 into that equation. So you can see, well, x becomes x0 and y becomes y0. So we get that equation, we get that form now. So that must satisfy, x0, y0 must satisfy that equation. So we'd sub it in, we'd find that side as the left-hand side is equal to the right-hand side. We do the same thing because the tangent of B goes through the point x0, y0 as well. So we can sub x0 and y0 into the equation for x and y. So our left-hand side should equal our right-hand side because x0, y0 lies on that point, lies on that line. Now, leave that for a moment. Consider an equation of x times x0, 2a y plus y is y0. Now, if we substituted a, which is x1, y1, into that, we get x0 times x1, 2a y0 plus y1. So notice we've got the y0 and the y becomes y1, x becomes x1. So we get that equation. Now notice, you might be saying, well, yeah, that's the same as that. Okay. So, and if we substitute x2, y2 into this equation, so the x becomes x2, the y becomes y2, so we get that equation there. And hopefully going, wait on, that's the same equation there. Wait on, how are we getting, what's happening with this one? So that's when we've considered x times x0 equals 2a y plus y0. And again, that's an equation of a line because that's x and that's y, so there's only an x and y in there, and they're just terms in that equation. So hopefully you've said that these are the same as the tangents. So basically what it does mean though, that both these points satisfy that equation, x times x0 equals 2a y plus y0. So if we're going back to the our line, this point and this point both satisfy an equation of a line. Well, if we have a look at what line they do lie on, it would be this line here, which we'd call the chord of contact. So if those two points satisfy the same line, that must be the equation of the line. So what is the equation of that line? It is x times x0 equal to 2a y plus y0. So, and you might be going, well, wait on, x times the x0, y0 is not even on that curve, on that line. It's not. But where the point of contact has, the tangents intersect, it does have a bearing on what the coefficients will be for this line here. And because x1, y1 and x2, y2 both satisfy that line, the equation of that line, that must be the equation of this chord there. So that's where we get the equation of the chord of what we call the chord of contact. So where the two tangents are contacting and intersecting, and we use that point of intersection. Hopefully that makes sense. If it doesn't, then go back to the start and have a go again and see if we can make some sense of it. As I said, it's a little bit freaky in terms of what it's asking you to do and the concepts there. Let's have a look at some questions involving this. So if we've got x1 and minus a is any point on the directrix of a parabola, we want to show the chord of contact has this equation. So what we're looking at here is that you've got our parabola, we've got our point on the directrix, x1 minus a, so that would be the case, and our chord of contact there. So if we drew tangents to that point there, so we would have the equation of the chord of contact, x times x0 equals 2a y plus y0. So we'd sub in x1, we'd sub in minus a, and that would give us x times x1 equals 2a outside of y minus a, because y plus minus a gives us that. So there's our equation there. Then hence show the chord of contact passes through the focus of the parabola. We'll show that it's a focal chord. Well, all we need to do is sub in 0a, put 0 in, put a, our left-hand side equals our right-hand side. And as we said, we're getting that chord of contact there. So it actually will, if it goes through the focus, it must satisfy, the focus would satisfy that equation. So it does, so we were able to prove that. So this time we've got a point T, which is 2at, at squared, be a point on the parabola. So there's our diagram. Always draw a diagram up if you're not sure. Okay, draw a diagram up. And then we start talking about tangent. So draw our tangent up, and we find the equation of that as that. So again, as we've done before, as I said, these are all exam type questions. So you'll get you to show the tangents there. So we find our gradient of our tangent, we sub it in, we get our equation there. And then if this tangent passes through x0, y0, show that, you can get that statement. So if it passes through that, well, x can be replaced by x0, y can be replaced by y0. So we get an equation there in at squared minus xot plus y0 equals to 0. So there's the equation that one is fine. Next part says, what's the condition for this quadratic equation in T to have two real roots? So if that's the case, if the quadratic equation is going to have two real roots, we know that our discriminant is greater than 0. So if that's the case, we get the x0, which is b, minus 4 times a, which was a, and c, which was y0. And that must be greater than 0. So we get x0 all squared minus 4a y0 greater than 0. And then x0 all squared is greater than 4ay. So what does that mean? Well, it means that the tangents must lie outside the parabola because it's not equal to. If it's equal to, then the tangents are on the parabola. So that line, technically would be on the parabola to be a tangent. So if we're sort of talking about the tangent here, that this line must be a tangent if it's equal to it there, but if it's going to have two real roots, okay, it's going to be a case where the tangent must be outside the parabola. So it must sit out, the point must sit outside the parabola there. It can't just lie on it. So that's what that one means. So the next question there, and then the next part, suppose that T1 and T2 are the roots of this quadratic equation, and capital T1, capital T2 be points on the corresponding to T1 and T2, show that the chord has that equation. Well, when we've got 2AT1, y is AT1 squared, 2AT2, AT2 squared. So if that's the case, find your gradient of that. So do the subtraction of the two terms here, subtraction of our x values. We're able to bring it down to T1 plus T2. And then we've got pick either of the points and we've subbed it in. We get it, ones that cancel out. So there's our equation that we wanted to find. And then show that these two must equal x0 on A, T1 times T2, y0 on A. So if that was our equation of our tangent before, and T1 and T2 are the roots of the equation, well, the sum of the roots would equal minus B on A. So as we get the minus of minus XL on A. And the product of the roots is Y0 on A because it's C on A. So there's how those two results come into play. Hence show that the chord T1, T2 has that equation. So T1 plus T2, that's of X equals 2Y plus 2AT, T1, T2. So we're able to do our substitution there because we're able to see the sum of the roots there before in the product as we had before. So we're able to do that substitution and then get down to the result we need. So it's just manipulating that algebra by being able to do that substitution. So there's a pretty complex problem if it starts to involve the chord of those. So we use all the results that we have as we go through and all different parts, but then now we start to use the relationships we do. Keep in mind we were told hence, so keep using the parts we've used previously. So if you're not sure about these ones, again, as I said, review it, but it is a reasonably complex kind of issue. So we need to make sure we can play around and manipulate all these equations to satisfy problems that we're going to face.